Hey there, class. Today we're going to go over lecture number 25, talks about concentration. We're going to tie in some of the concepts that we've been talking about with the stoichiometry that we've done before. So hopefully it'll start to kind of come together here for you. All right, let's get started. Okay. Oops, got a little lag. Oh, you saw the answer. All right, try and do this one on your own if you didn't see the answer. All right, so in the last lecture we talked about solubility. So hopefully you've gotten some practice using that table from the book, or you were able to kind of find another like mnemonic device or something online if that worked better for you. But you need to memorize the solubility rules going forward. So we can answer this question using the bottom, I think this is the bottom row of the table. And we're looking at, the quiz is asking us basically what's the state of the strontium sulfate and the beryllium sulfate. So we need to decide if this is aqueous or solid. And remember, aqueous is if something is soluble in water, and then a solid would be something that's insoluble. So sulfate is soluble unless it's paired with barium 2+, lead 2+, calcium 2+, or strontium 2+. So in this example, we have strontium 2+ with sulfate, so this one would be insoluble, so that's a solid. And then beryllium sulfate would be aqueous because beryllium is not one of the exceptions there. So D should be the answer. All right. Okay, so now we're going to talk about mixing stoichiometry with solutions. So here's an example of a question that you might be able to answer. And at this point, we haven't really talked about how to do this yet, but just kind of giving you an overview of what's to come. So you might have a question that says, how many grams of strontium sulfate are formed when 10 milliliters of strontium chloride solution are added to 20 milliliters of sodium sulfate solution? So we've done stoichiometry problems before where we're trying to predict how much or how many grams. So I'm trying to get my pen to work here. There we go. Okay, like how many grams of product are formed. And this one's asking how many grams of strontium sulfate is formed, right? But in order to do that, we usually start with grams of product. We can start with volume of product if it's a liquid, but we would need the density. And a pure liquid is different than a solution, right? A solution consists of more than one compound. So the question says, how many are formed when 10 milliliters of strontium chloride solution, right? So that's actually strontium chloride dissolved in water. So we really haven't learned yet how to do this because 10 mils of strontium chloride, depending on the concentration, it could contain 0.01 moles, or it could contain 1 mole of strontium chloride, right? Anything, we don't really know. What we would need to know is the concentration of each solution in order to do that. So adding even more to the stoichiometry map, I added this circle here and this circle here, okay? So the question was asking how many grams of product, so that would be grams of B, and we were starting with volumes of solutions. So in order to convert from the volume of a solution to moles of A, we need to know the concentration, just like we talked about. If we have the concentration, we can go to moles of A. If we have the chemical equation, we can use the molar ratio to go to moles of B. And for moles of B, we can go down to grams of B, right, using the molar mass. So adding these in, we should be able to convert from volume of solution to moles using concentration. Okay, so far we've seen two types of concentration. In the last lecture, we talked about solubility, which is basically the maximum concentration of a given substance. So for example, we said sugar was 300 grams per 100 grams of water, which tells us the maximum amount of sugar we can dissolve in 100 grams of water. So that tells us basically what the maximum concentration possible is for a certain solute. And we've also talked about electrolyte concentrations, where we've calculated milliequivalents per liter, and it's related to the concentration unit of molarity, which is what we're about to talk about. So in equivalents, right, one equivalent is 1 mole of positive or 1 mole of negative charge. So in order for us, in order for us to convert from volumes to moles, right, we need a different concentration unit. If we're converting from volume to moles, we're going to need a concentration unit that includes moles and includes volume. Currently, we have the solubility, which includes grams, okay? And then electrolyte is equivalence, relates equivalence in volume, okay? But we don't have anything yet that relates moles, purely moles and volume. So that's what we're going to need to get. And we're going to learn a couple other units of concentration in this lecture. Okay, so here's one of those units that you'll need to know, and you'll see this. This is the mass percent, and it's pretty simple. It's kind of, it's very similar to the solubility. It's the same units as the solubility concentration that we talked about. But remember, solubility is the maximum concentration of something. So mass percent is just the concentration of something at any point, basically. So this says how many grams of solute are there in 100 grams of solution. Okay, pretty simple, mass over mass. Sometimes you'll see it like this, m divided by m percent. You also have volume percent, which is what it sounds like, the volume of the solute over the volume of the solution. So that's just volume over volume. And then you have mass over volume percent, which is just the mass of the solute divided by the volume of the solution. So those are pretty self-explanatory. If you see mass percent, you know it deals just with mass. Volume percent just deals with the volume, and the mass over volume deals with mass over volume, right? Like the name really just tells you how to calculate it, basically. The one thing I think some people get messed up on is knowing that it's per 100 grams of solution. So it's not per gram of solution, okay? Or it's going to be over 100 milliliters of solution, basically. So the formula, again, yeah, is for all these is going to be the either mass or the volume of the solute divided by 100 grams or milliliters of solution. It gives you the volume percent. Okay. All right, let's move on. Okay, so go ahead and pause it and try and work this one out. Okay, so the question says an alloy of brass contains 65% copper and 35% zinc. Okay, so this is going to tell you, the problem is going to tell you what kind of concentration that is. So this is telling us that it is a mass percent. Okay, it's mass divided by mass. So when you see 65% of copper, and in this case, the solution is not in water, right? We learned about two definitions of solutions. One is like a solute dissolved in water or a certain liquid. Another solution could just be two or more elements that are mixed together. Okay, so an alloy, for example, is a solution, basically, of two metals mixed together. So the solution, if it says that 65% copper by mass, what that's saying is we have 65 grams of copper for every 100 grams of alloy, right, or solution. That's kind of what that's basically what it's saying, okay? So 65 divided by 100 would equal 0.65, right? And 0.65, if you turn that into a percent, would be 65%. So you can kind of see the relation there. Okay. All right, and then 35% zinc, right? So that would be similar, 35 grams of zinc for every 100 grams of alloy. Okay, if a brass tuba weighs 23 kilograms, which is 50 pounds, how much copper was needed to make the tuba? Okay, so let's go through this. So the brass tuba is going to be made out of this alloy, okay? And the question is asking how much pure copper was needed to make the tuba, okay? So if we start with 23 kilograms of brass, okay? And I'm gonna write it out so I can kind of talk through it as I go through it. 20 kilograms of brass. Brass is, again, the alloy. So maybe a better way to do this is to say 23 kilograms of solution, right? So solution is equal to brass in this case, right? Brass is the alloy, it's the solution, which contains copper and zinc. Okay, so 23 kilograms of solution, and we said 100 grams, or our units for our mass percent in the bottom is in grams of alloy or grams of solution, however you want to think about it. Okay, so we need to convert the kilograms into grams in order to use this. So we'll say 1 kilogram is equal to 1,000 grams, okay? And then in order to cancel out, now we have grams of solution on the top. We can use our mass percent and say 100 grams of solution contains 65 grams of copper, right? And that should, everything should cancel out here, and we're left with grams of copper, which is what the question's asking about, right? Okay. Okay. Okay, so in this question, I guess they leave it in kilograms. That's fine. You could just do that too. I think it's a little simpler. It would really depend on what the question's asking you to do. And here we would get our answer in grams of copper because we multiplied by 1,000. But if the question is asking for kilograms, you could then convert that grams. Or because 65 grams of copper, since the mass percent is 65% copper, then really if you just multiplied this number by, we're looking at kilograms. Yeah. Let's see, yeah, if you converted both of these to grams, you would basically, you'd say 1 kilogram over 1,000 grams. That would convert the top to kilograms, and then you could do the inverse, and you could get your answer that way. But it doesn't really matter, and the zeros cancel out. I'm sorry, I'm just trying to think of a way to like mathematically prove that this is true, but I think it's going to be more complicated than it's worth. So hopefully you can see the relationship that it doesn't really necessarily matter if these are in grams or kilograms. I like to keep them in grams just because it's like more consistent. And if you're confused by this way and this way made more sense, just do it this way and you'll be fine. Okay. Go ahead and try this one out as well. Okay, so this one says common rubbing alcohol can be 70% isopropyl alcohol and 30% water. So that's the volume percent. How much alcohol is in 25 milliliters of rubbing alcohol? Okay, so if we have 25 milliliters of rubbing alcohol and our volume percent is 70% isopropyl alcohol for, sorry, not 70%, 70 milliliters. Sorry, I wish I could erase on this. 70 milliliters of isopropyl alcohol for every 100 milliliters of solution, which in this case, our solution is the rubbing alcohol, right? That's the mixture of isopropyl alcohol and water. You do that calculation and you should get your milliliters of isopropyl alcohol. Okay. This last one shows a mass over volume percent. So in this case, it says the salt solution is 25% sodium chloride mass over volume percent. How many grams of salt are in 200 milliliters of this solution? Okay, so by definition, mass over volume percent, since it's 25, it tells us that we have 25 grams of sodium chloride for every 100 milliliters of solution. Okay, so we can use that just like we did before. We have 200 milliliters of solution. We use the mass over volume percent, and then we get our grams of sodium chloride using it that way. So we won't use these three concentrations that much in this class. I mean, you'll see them, so you need to know them, but it's more of like a real world application. These actually get used a lot more in the real world than they do in chemistry. So it's just good to know. All right, pause the video and try and do this one as well. Okay, so you mix together 25 mils of isopropyl alcohol and 36 milliliters of water. What is the volume over volume percent of isopropyl alcohol in this mixture? Okay, so we have 25 milliliters of isopropyl alcohol divided by our milliliters of solution, right? Because it's asking about the volume of isopropyl alcohol. So 25 plus 36 would be our total volume of solution. So that would be 61 milliliters of solution. Okay. So if you did this calculation, and again, the volume over volume percent, we need to have it in terms of milliliters of isopropyl alcohol divided by 100 milliliters of solution. Now there's a few ways you can do this. The way I like to do it personally is I divide these numbers, and then so divide these numbers. Let me pull out a calculator. So you have 25 divided by 61. Okay, so that tells us we have 0.4, about 0.41 milliliters of isopropyl alcohol. And what this does when you divide the numbers is it normalizes the bottom to 1 milliliter of solution. Okay, and yeah, if you want me to go over the math, I could, but anyway, I think the PowerPoint might show you a different way to do this. This is kind of how I like to do it. There's like a formula you can memorize to do it. Again, I just kind of like to use units because I don't have to memorize any formulas. But anyway, so you normalize this to 1 milliliter, and this is what we need to get to, right? So we need 100 in the denominator. So in order to get 100 down here, right, we need to multiply by 100 on the bottom. But we can't just multiply by like 1 over 100, right? That'd be changing our number. But you can always multiply anything by 1, and it is itself, right? So if we multiply it by 100 over 100, then we're not really essentially changing this number because we're multiplying by 1. And if we multiply the top by 100 and the bottom by 100, we have 41 milliliters of isopropyl alcohol divided by 100 milliliters of solution, which tells us that our volume over volume percent is 41. So you divide these numbers, and then you get 0.41. You get what you got before, and it would be 41%. So there's Uh, yeah, I think the easier way, like using the formula, is just going to be like you divide it and then you see 0.41 and then you multiply that by 100 and you get the percent. Um, that might be the way that most of you want to do that. It's probably easier. You're probably wondering why I did this. It's probably more complicated, but it just helps me personally see that I got it right as I'm moving through the question. So yeah, so the formula is basically divide the milliliters of solute divided by the milliliters of the solution, multiply by 100%, and you get the percentage. Anyway, this is just kind of my way to like see it, and I don't memorize anything. And anyway, either way is fine. Okay, so the general formula, which is actually on the slide, I think it's a couple slides up, is the volume of solute divided by the volume of solution times 100%. Okay, that's how you get the formula. I'll go back to it to show you guys. Okay, so this shows all the formulas. So for mass percent, it's grams of solute over grams of solution times 100%. Volume is volume over volume times 100, and mass over volume percent is grams of solute over milliliters of solution times 100%. Okay. All right. Okay. So for chemical reactions, we don't, like I said, we don't use mass over mass a lot or mass over volume. But because chemistry, we use a lot of moles, right? Moles is a huge unit that we use a lot. So for chemistry, we're going to need a number that allows us to convert from volume to moles, right? I talked about this before. We need volume to moles. So that means our conversion factor or concentration needs to have these two units. So the conversion factor that we use in chemistry is moles of solute over liters of solution. So before we saw, mass of solute over mass of solution, or mass of solute over volume of solution, right? We've seen all those. In chemistry, and what we're going to use mostly is this moles of solute over liters of solution, okay? And the name of this is molarity, and it's denoted by like a capital M, okay? Sometimes the M is like italicized a little bit, but big M is molarity. Sometimes it has a line under it too. So anyway, let's look for the big M. All right. Okay, again, so this N is always kind of meant moles, right? When we went over gas laws and stuff. So moles over volume, right? Moles of solute over liters of solution. And that liters is actually important. Okay, we saw in that example where it didn't really matter if we used kilograms or grams. That's only true if the top and the bottom numbers have the same unit, okay? For molarity, it needs to be in moles and it needs to be in liters, okay? In order to calculate it correctly and to use it correctly. All right. Another way you'll see this is just with brackets. So you might see something that says like the molarity of chloride would be in like Cl minus, something like this. And it's going to equal 0.10, and then you'll see M with a line under it, or just a big M maybe. But the brackets mean the concentration of chloride in units of molarity. Okay, that's what the brackets mean in chemistry. Okay, so going back to the stoichiometry map, we've defined now this concentration. Okay, this is going to be concentration in terms of molarity. Okay, again, that takes us from moles to volume, right? And that's what we're going to be using to do this conversion. Okay, so here's an example of molarity. So this says and the correct terminology when you're reading these things would be, if you're reading something like this, it says a 1 molar sodium chloride solution is prepared. Okay, so sometimes you'll see the word molar, like 1 molar sodium chloride solution is prepared, and that just is refers to molarity. Okay. So in order to do that, we need 1 mole of sodium chloride, right? If this is going to equal 1.0 molar, that means we have 1 mole of sodium chloride. in 1 liter of solution, right? 1 divided by 1 is 1, okay? So in order to prepare that, you're going to weigh out 1 mole of sodium chloride, which you could convert to grams using the molar mass, and it'd be 58.5 grams. And then you add enough water to get up to the 1 liter mark, right? This is 1 liter. Okay. So it's not 1 liter of water and then you add the sodium chloride. It's 58.5 grams of sodium chloride and then add enough water to get to 1 liter, right? Because this is 1 liter of solution, which means solution includes the water and the sodium chloride. Okay. All right. We kind of talked about this, how units of molarity can help us convert between volume and moles if we're dealing with solutions. So here's an example. How many moles of sodium chloride are in 25 milliliters of 2.5 molar solution? So if you look at the stoichiometry map, here we're going from volume of A to moles of A. And if you remember, if this volume is a solution, to convert from volume to moles, we're going to use the molarity, right? So if we want to line up units, which is, I think, a really good way to think about this, remember that 2.5 molar, if you wrote this out, it would be 2.5 moles of sodium chloride divided by 1 liter of solution. Okay, so if we have 25 milliliters of solution, we're going to say, okay, we have 25 milliliters of solution. And then if we put liters of solution on the bottom, or I guess, sorry, first we have to convert to liters. So we would say 1,000 milliliters is 1 liter. And then we could use, kind of get that out of the way, 2.5 moles of sodium chloride for every 1 liter of solution. Okay, so milliliters cancel out, liters cancel out, and we're left with moles of sodium chloride, which is what the question's asking for. Okay, perfect. So if you like formulas, you could use this one right here, right? This is telling you that the number of moles equals the concentration, so the molarity, times the volume. And that's what we did here, right? So we said, okay, this one again, this converts the molarity in terms of moles per milliliter. In order to do that, you have to change some numbers though. So I think this is easier personally, kind of lays it all out. But you could say, right, we're given that you have 2.5 moles of sodium chloride for every 1 liter of solution. So that's the same as saying 2.5 moles of sodium chloride. 1 liter is equal to 10 to the third milliliters of solution. And so that's what that's what the PowerPoint shows here, okay? But if you like walking through it step by step like I do, I think that's a good way to do it. Or if you just want to use the formula, you're going to take the molarity times the volume, but you just have to make sure the units match when you do this in order to get the moles. Okay, so anyway, you can use any of these 3 equations if you want to memorize all 3 or 1 and learn how to, they're all the same thing, they're just rearranged like with algebra. I think it's easier to just think of it in units, in terms of units. So I'm kind of showing that, but this question says, what volume of a 0.36 molar solution of potassium iodide is needed to provide 0.25 moles of potassium iodide? So in this case, we're actually looking for volume. So if you use the formula here, volume is equal to the number of moles divided by the concentration, right? So you would take, basically you just take 0.25 moles of potassium iodide and divided by the concentration, which in this case is 0.36 molar, and that would equal your volume, right? The way I like to think about it is I'm starting with 0.25. The reason I like to do it this way is because we've been doing conversion factors this whole class, and that's all this is. And so I'm just trying to show you that it's really the same thing we've been doing. I don't like memorizing multiple equations, so I prefer just to do it the way we've kind of done it before, using conversion factors and canceling out units. So we're starting with 0.25 moles of potassium iodide. We know that this number right here, 0.36 molar, really just means 0.36 moles for every 1 liter. Okay, and then that's a conversion factor we can now use. We need moles on the bottom to cancel this out. So we say 0.36 moles of potassium iodide in 1 liter of solution. Okay, and then the moles cancel out, and we're left with liters of solution, which is what the question's asking for. And you can see that this is really the same thing as this at 0.25 divided by 0.36, which is what we had using the formula. I just think it's easier to see using the units that you see here. Okay. Either way is fine with me. Okay. Go ahead and pause the video and try this quiz. I put the stoichiometry map up in the top left because I think it can help, and I think a lot of you are using it, so that's good to know. All right, so the question says, how many grams of aluminum chloride are needed to prepare 125 milliliters of a 0.15 molar solution? Okay. So we're gonna say that the solution here is our A, and aluminum chloride, oops, is our B, okay? So we need to know how many, let's see if the map will work on this one. I think it should work. Okay. So I'm just gonna read the question to make sure. I need to prepare. Okay. I'm not sure if, yeah, the map still kind of helps, but I think we're gonna have to think of it a little bit differently. So this is a solution of aluminum chloride. So basically, both of these are kind of A. You can bear with me here for a sec. We're starting with volume of solution. And so in order to get to grams of aluminum chloride, which we need, we're going to use this moles. The reason we're not using a molar ratio is because this isn't like a chemical equation. That's usually when we use that, is if we're converting that way. And if maybe the map isn't super helpful on this one particularly, if it is, great. If not, just ignore it, and I'll kind of just walk you through it. So in order to get to grams of aluminum chloride, right, we need to know how many moles of aluminum chloride do we have, right? If we have moles of aluminum chloride, then we could easily figure out grams just using the molar mass, okay? And the only way to figure out moles of aluminum chloride is to use the volume and the concentration. Okay, so the equation you could use is N equals concentration times volume, if you want to use the formula. The way I would do this problem is say I'm starting out with 125 milliliters of solution. Okay, I'm going to convert my milliliters to liters because that's the units that are in molarity. So 1,000 milliliters for every 1 liter. And then our molarity tells us that we have 0.150 moles of aluminum chloride, aluminum trichloride, I should say, for every 1 liter of solution. And then we can convert from moles of aluminum chloride into grams of aluminum chloride using the molar mass of aluminum chloride, which I don't know off the top of my head. What is it? 133.5 grams for every 1 mole. Okay, so milliliters cancel, liters cancel, moles of aluminum chloride cancel, and we're left with grams of aluminum chloride. Here's kind of another map. This is saying concentration and volume goes to moles and then to grams. That's kind of what I'm showing here with the map. You go from volume to moles down to grams. So in this case, we use the concentration here, and then we use the molar mass to do the final conversion. So it's really not like using the map like we usually do, but I think the map, even in this problem, helps because it says, okay, how do we get from volume to moles? Well, we need the concentration, which is the molarity. We have that. And we can get from moles to grams using the molar mass. Okay, so do all those calculations. And this one just breaks it up. So it goes from volume to moles. So it does this first step, volume to moles, using the concentration. And then from moles to grams using the molar mass. All right. As you can see, there are many ways to tackle these problems. And I'm sorry I don't like fully in depth cover every single way. I like to just show what I'm most comfortable with because I personally believe it's the easiest way, but that could just be me. So I'm going to briefly talk about other ways as well, because I'm sure if you don't like the way I do it, then you can do it one of these other ways too. Okay. All right, here's another example. Go ahead and try this one. This one, I believe, you will use like the stoichiometry map, like we normally see. Okay. How many liters of hydrogen gas are produced at STP when 125 mils of a 6 molar hydrochloric acid solution reacts with excess zinc? Okay. So in this one, there's some crazy stuff going on, and we are combining a lot of ideas. So probably noticed on the exams that some questions are like just one idea, right? It's like convert moles to grams or something. Super easy. That's just molar mass. But then there's other questions like this where it's pulling information from like all throughout the semester, okay? And these are the more challenge problems, I guess you could say. Okay, so first thing we're going to need to do, this is obviously a stoichiometry, sorry, I shouldn't say obviously. If you didn't know, don't feel bad. It's really not obviously a stoichiometry question. This is a stoichiometry question. There's a reaction happening, which means we need to write out a chemical reaction in order to solve this. Okay, if there's ever a hint of a reaction going on, chemical reaction would be the first place to start. So it tells us that hydrochloric acid reacts with excess zinc. Okay, so HCl is going to react with zinc. Okay, zinc is a pure element, so it's just on its own. It's not diatomic or anything. And it already tells us that hydrogen gas is produced, so that gives us one of our products. And so you can see this is actually like a single displacement reaction. Yeah, single displacement. And so if our hydrogen is going to be on its own, what we're left with is zinc and chloride. And luckily those will form a complex here. Okay. Let's see. What this doesn't really tell us is the charge on zinc, right? So this could actually be zinc Cl2, or it could be zinc Cl4. So if I'm in a test and I'm answering this question and I don't know which one it is, right? I don't know what the charge is on zinc, so I don't know what formula to use for the product. Just move on at this point and we'll see if it even matters, okay? All right. Okay. So let's balance the equation now. And this is where it might matter, right? Let's just look at two different examples, okay? Let's say it's zinc Cl2. Or let's look at another example and say, I don't know, maybe it's zinc 4, and so it would be zinc Cl4, right? Something like that. So the first example, we're going to have 2 hydrochloric acid molecules, right? Because we have 2 hydrogens here. That gives us 2 chlorides, we're good, and then we have 1 zinc, so we're balanced just by using that 2. If there's a 4 here, right, we might put a 2 in front of this HCl, but we actually, since there's 4 chlorides, sorry, we actually need a 4 in front of this HCl, right? And then we would need, since that's 4 hydrogens, we'd need a 2 here. So it's kind of like, regardless of what we do with this zinc, the ratio between hydrochloric acid and hydrogen is the same. It's 2 to 1 here, and it's 4 to 2 here, and 4 to 2 is the same as 2 to 1. So it really doesn't matter which one we use. Obviously, if we were doing a ratio between like hydrochloric acid and zinc chloride, here it's 2 to 1, and here it's 4 to 1. So we wouldn't even have enough information to really answer this problem. But luckily, we don't need that, and that's why the problem doesn't really give it to you, is because either one, it's going to work out. I think on a test, I would definitely give you like what this other product's going to be, just to eliminate a lot of this guessing. But people have been complaining, sometimes not complaining, people have been saying that the lecture problems are sometimes a lot easier than the actual problems. So here's an example where this is probably harder than anything you'll see on the test. Okay. Now, moving on to the question. How many liters of hydrogen gas are produced at STP? Okay, so we're looking for a volume of gas at STP, which is right here. That's what we're looking for. When 125 mils of hydrochloric acid solution reacts. So we're starting with the volume of a solution, okay? So we're gonna have to go from volume to moles, from moles over to moles of B, and then down to volume of B. Perfect. All right, let's do it. So we're starting with the volume. So we have 125 milliliters of HCl, of solution, right? And then we can use our concentration to convert from volume to moles. And since this is in milliliters, we're gonna have to change that to liters. Okay, so then we can say we have 6.0 moles of HCl for every 1 liter of solution. Okay, so at this point we've converted from volume to moles because we're at moles of HCl now. Now we need to go from moles of HCl to moles of hydrogen. It doesn't really matter if you use 2 to 1 or 4 to 2, it's the same ratio. But I'm just going to say 2 moles of HCl for every 1 mole of hydrogen gas. Okay, so now we've gone from moles of A to moles of B using the molar ratio. And now what we need is to use, since we're at STP, we can use 22.4 liters per mole. Okay, so for every 1 mole of hydrogen gas, it occupies 22.4 liters. And that gives, let's see, milliliters cancel, liters cancel, moles of HCl cancel, moles of hydrogen cancel, and we're left with liters. The question says, how many liters of hydrogen gas? Okay, we got our answer. All right, yeah, this one uses zinc Cl2. Again, if this is like on a test, you could totally see this problem on a test, but I would have probably tell you that if, I'd probably just give you the equation or something like that, because this would be hard to know. It's not really one of the ones in the first 2 columns, so, okay. All right, and then, let's see. Sorry, 1 second. Okay, I'm back, sorry. I just had this thought about, I was remembering that zinc actually always has a 2+ charge. So I was wrong in saying that it could have a 4+ charge. For some reason I was thinking it was one of the transition metals, and it is, but it's one of the ones that always has a 2+ charge. But even then, I think I'd probably just give it to you because obviously I can't even remember what the charge is on zinc, so that would be more of a challenge. So disregard all of that stuff that I was saying. And anyway, here we go. So, sorry. Okay. Oh, we already made it through the problem. Back up. Have the slide direct you because the slide's more correct than me, obviously. Okay, so we got the balanced equation like we saw, and then this is the pathway, which you could also see through the stoichiometry map. And this is going to kind of solve it piecewise, where we first convert from volume to moles, then from moles of HCl to moles of hydrogen, and then convert over to volume of hydrogen gas using the 22.4. All right, still got the right answer, so we're good. Okay, last concept we're going to cover in this lecture is about dilution. So dilution would be, this is a pretty clear example here. You have this solution at some concentration, right? And then you add a bunch of water to it. Well, the particles of color, whatever this color is, are going to spread apart because there's now more volume but there's more volume of water, but the number of particles actually hasn't changed. So what happens is that the concentration of the solute decreases, right? Because concentration is the moles divided by the volume, right? So if the number of moles of solute doesn't change, but the total volume of solution increases, then the total molarity is actually, or the concentration is going to go down. Okay. All right. So, and we talked about that. Moles of solute haven't changed, only the volume and the concentration change, right? So in that case, we can say that N, the number of moles, is a constant. And if it's a constant, we've kind of seen this before with the ideal gas laws, then that means that concentration and volume at any point would equal another concentration and another volume at another point, right? Because they're related by the number of moles, which are constant. And that's where we come up with this dilution equation. So an example of a problem you might see with these says that 20 milliliters of water is added to a 10 milliliter, 2.5 molar sodium chloride solution. What is the final concentration? So here is our initial volume, right? And this is our initial concentration. And this is our 20 milliliters is added. So our V2 is actually going to equal 30 milliliters, right? Because this is total volume, okay? So now we have 3 of the 4 unknown variables, and we can plug it in and solve. So again, so this is initial volume, this is final volume, because you add 20 mils to 10 mils, you're going to get 30 mils. And then you multiply by the initial concentration, and you're going to get the final concentration. Okay. All right, cool. All right, go ahead and pause the video and use that dilution idea that we just talked about to try and answer this question. All right, so the problem says you have 500 milliliters of a 2.0 molar solution of sodium hydroxide, but you want a solution that is 0.25 molar. How much water do you need to add? All right. So if we read through the problem here, this kind of like, I like to answer these kind of like I did the gas laws, where I kind of like label everything as I move through. So it says you have 500 milliliters, so that means that's our initial volume of a 2.0 molar solution, that's our initial concentration. But you want a solution that is 0.25 molar. So we actually want a concentration of this, so that would be our final concentration. So if we look at the dilution equation, then we're actually searching for V2, right? Okay, and we'll talk about this in a sec, but let's solve for V2. Okay, so we have initial concentration divided by the final concentration, and this is just rearranging the dilution equation. Multiplied by the initial volume, and we get 4,000 milliliters, right? That's our final volume. The question, so you may have been tempted to select 4 liters. The question though asks, how much water do you need to add? And so we need a total of 4,000 milliliters, but we already started with 500 milliliters, right? So we take 4,000 minus 500, that tells us how much we actually need to add, okay? So final minus what we already have gives us 350 milliliters, sorry, 3,500 milliliters, which is 3.5 liters. Okay. All right, here's another example for some more practice. If you want to pause the video and try this out. Okay, so it says we have 10 mils of a 2.5 molar beryllium chloride solution, and you're mixing it with a 20 milliliters of a 1.0 molar potassium chloride solution. What is the final concentration of chloride ions? Okay. All right, so let's walk through this one. So one way you could do this, which is kind of just at first glance, this is how I probably would solve it. 'Cause, I don't know, it's the way I like to think. So it says we have 10 mils of a 2.5 molar beryllium chloride solution, and we're mixing it. So beryllium chloride is soluble in water, right? So if we put beryllium chloride in water, it would dissociate into beryllium and 2 chloride ions. Right? If we put potassium chloride in water, it's also soluble. It would dissociate into potassium and chloride ions. So if I use the stoichiometry map, I can go from volume of beryllium chloride solution over to moles of beryllium chloride in just 2 steps. So I can say I have so 10 milliliters of solution, right? And I convert my milliliters to liters, and I multiply by the molarity. Sorry, that's a 2.5 moles of beryllium chloride over 1 liter of solution. Yep, and then that gives me moles of beryllium chloride. And then we can convert over from moles of beryllium chloride. We know the molar ratio. 1 mole of beryllium chloride produces 2 moles of chloride ions. All right, and that's just using the molar ratios from the equation. Okay, we do that and we're left with moles of chloride ions, right? We can do the same process with the KCl and we'll get moles of chloride ions that were given by the KCl as well, right? Then if we're looking at the final concentration of chloride ions, we can just add up the moles of chloride and divide by the volume in terms of liters, and we should get the molarity. Okay, so that's one way to think about it. Again, so we need the total moles of chloride and the total volume. So that's what's happening here. We're doing volume times molarity and then converting from moles of beryllium chloride to moles of chloride. Do the same thing with the KCl and we get total moles of chloride from the KCl. If you add those two together, it's telling us that our total moles of chloride ions in solution is 0.070. Then if we divide, our total volume is 30 milliliters, right? And then if we divide moles over liters of solution, so if you convert this 30 milliliters, you would have 30 times 10 to the negative third liters, which is what we have down here, right? So we have moles of chloride over volume. That gives us our total chloride concentration, which is 2.3 molar, okay? All right, that last question was a little harder too. It's kind of testing your understanding of molarity and all that stuff. So keep practicing. I know it's kind of getting crazy. There's a lot of ideas coming together. So a lot of practice will be helpful. And, you know, please come to office hours. If you have questions, don't just sit there. Come to office hours or go to those virtual TA office hours that I posted up there. Should be in an email that I sent, or Promote has office hours. So I'm hoping there's like plenty of opportunities for you guys to get help if you need it. And send me emails. Anyway, don't be afraid to ask for help as these ideas kind of get more complex and we're putting more together. it can get a little crazy to like keep track of and manage. So, all right, I think that's it for this one. We'll see you next time.